has started.
Yes, so hello everyone, and thanks Nils for inviting us. This presentation is about SDO, the Scheduled Data Ontology, how this work is progressing as part of the OBI IDO framework. And as Nils mentioned, please ask your questions after the presentation or write questions in the chat during the presentation. This session will give a high-level overview of the work we are doing on scheduling and the scheduled data ontology, how it's being developed and applied in practice. So we're actually 5 presenters here today, working across companies and disciplines, all members of the same team. So we will take you through different parts of the work. First, scheduling fundamentals by Erik Danielsson from Promineo. Then the SDO standardization project that my name is Lillian from DNV, will present, followed by the main concepts and alignment with IDO by Mihaly Fekete from Equinor and Dirk Walther, DNV. And at the end, Erik Danielsson from Promineo will give some information about the implementation and use of SDO. At the end, we will have some concluding remarks. So the project is funded by the operator companies Equinor, Aker BP, and Vår Energi through Cooperate, formerly Offshore Norge, and led by DNV. It's carried out in collaboration with Promineo, Equinor, and the SMEs, scheduling subject matter experts from these operating companies. And that, Erik, I think I'll hand over to you to start the introduction and say a little bit about scheduling.
Thank you, Lillian. I'm Erik Danielsson, and I am responsible for support and implementation of the new ShedX solution, the cloud solution that I will be talking a bit about. And I've been working for a scary number of years, almost 28 years, with plan and schedule data in some form or another, and trying to make sense out of it, making it, visualizing it, and trying to extract useful information from it. So this is a pretty natural extension of that work. So I will try to give you a sort of a crash course in scheduling for a few minutes, 10 minutes, I believe. Let me just start the timer here so I don't mess up. There we go. And the first thing I want to say is just a big sort of a history of why did this start, this whole initiative? And about 15 years ago or so, it was estimated that each year in Norway, about $500 million is used because you have to double and triple punch the schedule data from one system to another across the company borders and even within company borders. So it was a huge waste of resources that was used for this purpose. So it was decided we should try to create a standard, an ISO standard, so we can represent schedules in a neutral format and just translate those into that format and import those neutral formats into the other scheduling system. So that was about 9 years ago. This ISO standard was first seen, called 15926 part 13. And the current solution, or rather, we had a solution working. There was a prototype version, a desktop version that could convert the schedule to an ILAP file, we called it, and then it could be imported into a scheduling system, another receiving system. So that was in use for several years before this current solution, which is now 1.5 years, I believe, or so. And it's a cloud-based solution for transferring schedules. You can actually schedule, let's say, Tuesday, 5:00 p.m. That schedule enabled should be transferred to Equinor into their schedule. So that's now been used in over a year. So I just want to talk about what is a schedule and what does a scheduling tool do. And I guess, first of all, the difference between a schedule and a plan, that could be interesting. That's a philosophical, ontological question we can just dwell a moment on. A plan is when you have an intention of achieving something, and the schedule is when you set dates for those things that you want to achieve. So a plan is just a list of activities you want to complete, but once you have dates on them, then you have a schedule, very simply put. So what you do here, you just list all the activities you want to do, and very importantly, you assign links between these activities. So that when this one starts, the next one can continue. And then you can just press a button and generate these dates according to an algorithm. We'll talk a moment in the next slide. So it's quite important to understand that there is a algorithmic aspect of any scheduling tool that's highly essential. It's cannot do without. This little schedule here is just like 11 activities, but we operate now with over 100,000 activities that spans multiple years, and we are transferring those using the solution. And some of these schedules are populated by up to 20, 30 different smaller schedules into one big master schedule. So it's quite a lot of data that's already flowing. We'll have a number on that in a second in the end of the presentation. So let's just talk a bit about the Dijkstra algorithm used to create these dates. And you have each of these nodes represent an activity, and each of these numbers represents a duration. So it takes 6 days to go from A to B. And then you try to find the shortest path through that network. And that is, you go from left to right and find the shortest. That's the forward pass, and then you make a backward pass once you reach the end. And then you can have 2 sets of dates, one early set and one late set. And the difference between those two for each activity indicates how much wiggle room, so to speak, each activity has. It's called the float. And if an activity has 0 float, then it is on the critical path of this schedule, meaning that it cannot be delayed without delaying the final project date. So that's an important concept for planners, the critical path with 0 floats. So I'm just highlighting one aspect here because Dirk is going to talk a bit about this in a moment. And it's this link here. It looks a bit longer than all the other links. And that is because we can assign something called a lag, 5 days in this case. So that when this starts, we have to wait 5 days until the next activity can start. So we have these links can have 4 different types: finish to start, the most common one, finish to finish, start to finish, and start to start, all the permutations. And the link, as we said, can be assigned a lag. But this is when this sort of complexities start appearing. In Safran, we can see here, you can also assign a calendar or work pattern. So that these 5 days, these 5 working days, according to that calendar, is when you find out the date of this next activity. And that is unique to Safran. Safran is the only tool that can have a calendar assigned to a link. So we will now move into this challenge we have in schedules that are behaving differently. One scheduling tool, for example, Safran to P6 does not have a link possibility or a calendar or work pattern for a link. It can only reference the successor activities calendar or the predecessor activities calendar. You can configure that, but you cannot have a specific calendar assigned. So this thing about interoperability it's a fancy, nice word. We want to be interoperable, but it's a relative term, and it's a messy term because, and I will give you an example, even if we only have Safran to saffron transfers. We don't even cross the boundary of one schedule to another. We still have no guarantee that you get the same dates from the scheduling engine. And why is that? Well, here's an example. This activity, we have said that duration stretch is controlled by the project setup. So this is, we have stretch or no stretch. That's a very major thing. Can the activity duration be stretched according to this engine? Can it allow it to stretch? And if you export this with no stretch and you import it into a saffron with stretch, you will get very different results. So you see, it's starting to get complicated. And one of the sort of self-defense mechanisms we have against this interoperability challenge is we can say, okay, I want to guarantee that the dates are the same in the receiving side. So I can map in the tool, you can actually say that the early start should be mapped to must start on, and the early finish should be mapped to must finish on to ensure that it's the same date. And you sort of bypass this scheduling engine in a sense. So I think I'm running out of time pretty much. So I will just quickly wrap up and say that each week we have about 3 to 4 million activities transferred by ShedX. And as I mentioned, some of these have close to 100,000 activities. So we can see on this graph for different companies, we have Aker BP, Aker Solutions, Equinor, and Able, totaling about between 3 and 4 million activities per week when we do these transfers typically. You can do it on a monthly basis, but in most cases we do it weekly here. So I think if you have any questions to this, you can get back to those at the end if there's time. So I'll just hand it back to you, Lillian, and you can continue.
Yes. Thank you, Erik, for that nice introduction. Now I'll briefly introduce you to the SDO standardization project. It is being developed as part of the OBI standard series, ISO 23726. The purpose of SDO is to provide a standardized way to represent schedule data so that it can be consistently understood, reliably exchanged across tools and organizations. So it's important to highlight also that the aim is not just to define a model, but to enable interoperability in practice. Some of you might be familiar to this figure from earlier. It is taken from the IDO presentation in this training session series. So SDO is one of the domain ontologies within the broader framework for ontology-based interoperability. And in fact, it's actually the first domain ontology in this standard series. And it's the part 100. The work we are doing has given us a good opportunity to both align with the principles defined in IDO, plus provide feedback back into the development of the standard series based on this practical experience. So in this sense, the work we do on SDO is closely connected to the overall development of the OBI framework. But then, why are we doing this? Erik has already now mentioned a lot of practical examples, some of the complexity from this domain. And we see that there is a lack of consistent understanding of schedule data across tools and companies. And this is leading to challenges when you exchange schedules. There is also limited interoperability between scheduling and other domains, for example, maintenance, procurement, and asset models. So the motivation for SDO is therefore to enable more reliable data exchange and to support semantic interoperability across these domains. Yeah, and as this is an ISO standardization project, there is a formal process to follow. The project itself was formally approved early 2025, but the work itself has evolved over several years. We received the committee draft consultation comments earlier this year, And we are now approaching submission of the draft international standard, the DIS. This is expected after the summer. So that means we're actually moving into the final stages of the standardization project. What we see is that we have had strong engagement within the ISO community with the nominated experts. We have contributors from multiple countries, and a significant number of comments have been received through this process. The work we do brings together different types of expertise. We have scheduling domain expertise from senior planners, ontology and semantic modeling expertise, and also implementation and software expertise. We think that this combination is very important to ensure that the ontology is both theoretically sound and practically applicable. And related to this, we would also like to acknowledge the strong collaboration across companies and thank all the contributors involved. You can see the companies listed here below through their logos and company names. And with that, Mihaly, I'll hand over to you to go through the SDO concepts.
Thank you very much, Lillian. So I take over the presentation here. So my name is Mihaly Fekete, and I'm working as principal data architect at Equinor in the technology development innovation department, and has been a member of the team developing the scheduled data ontology. So in the next few slides, I will focus on main storyline of SDO ontology and how it aligns with the industrial data ontology developed in the OBI framework. The key message is that SDO is not only a vocabulary for exchanging schedule data, but is a semantic model that places schedule concepts into a broader industrial ontology. So the main concept, the central concept, as Erik already described, is the schedule. And the schedule represents the overall plan, a time sequence structure of the work to be performed. It organizes work through schedule activities and milestone activity instances. The schedule activity represents planned work carried out over time, while a milestone represents a significant point in the plan, such as a start or a completion or a decision point. These activities, these work items, are connected by a schedule activity link as a next important entity in the ontology. Or we can think about it as a schedule activity dependency. This captures the logic between activities and milestones. For example, that one activity must finish before the other can start. And in addition to that, SDO represents resources and how those resources are aligned with separate activities. A resource describes the resource need, while the assignment connects the resource to a specific activity. So around this core concepts, it includes as well effort, progress, work pattern, and resource profile. So together, those main concepts describe what work is planned, what it can happen, and what it depends on, what resources are needed, and how progress is tracked in the schedule. So the next point is that those concepts are organized as formal ontology classes. Those classes are not just informal terms, but they are machine-readable OWL classes with their definitions, with their properties, and with their relations. And SDO also provides the more specialized scheduling concepts. As an example, a schedule can be specialized as a baseline schedule or a live schedule. Or dependencies can be specialized into standard link types, such as the finish to start, finish to finish, and so on, as Erik already talked about, and those reflecting the logic used in the planning systems. So resources are specialized as well, as they can distinguish between labor resource, material resource, or non-labor resource, such as a tool or equipment, and information resources such as permits, reports, or technical documentation. This really matters because real schedules are richer than activities and dates. They include dependency logic, resource needs, planning assumption, and progress information. The most important architectural point for us was the alignment with the top-level ontology IDO. SDO does not define scheduling concepts in an isolation. It places them right under the IDO classes like activity, event, object, or information object. So for example, schedule and schedule activity are aligned as subclasses of the activity IDO class, main class, meaning that schedule work is treated as something that occurs over time. Milestone is aligned as a subclass of event, which fits into the idea of a significant point in time. Schedule resource is aligned under the object class, with specific resource types could be aligned to the relevant IDO classes, such as a person, a compound, or an inanimate physical object. The alignment enables interoperability beyond scheduling. It allows us in the future to connect schedule data with asset, maintenance data, procurement, and commissioning information in the same semantic framework. So SDO then uses as well object properties to connect those classes or instances of those classes as relations, as we know. A schedule has schedule part, for example. Activities can have predecessors and successors. Resources can be assigned to activities. Activities can have start times, finish times. They can have work patterns, efforts, and progress. The model also defines domain and range restrictions, so relationships are used consistently. Inverses are useful because the same relationship can be carried in both directions. For example, from the predecessor to a successor, or from the successor back to the predecessor. So finally, SDO represents the schedule attributes through data type properties. This captures the values such as dates, durations, progress percentage, effort value, the lag, float, and working hours. Key distinction is whether a value is planned, calculated, or observed. So there are the main qualifications of the properties. Planned values are specified in advance. Calculated values are produced by a scheduling engine, for example, and observed values are captured during the execution, such as actual start or actual finish or actual progress. So those are the main concepts for or the main resources in our overall perspective, what I would like to provide you, and we will have some specific example Dirk can go through to exemplify how those are implemented in the ontology. So I'm give you the word on the screen, Dirk.
Are you muted, or we cannot hear you? You are sharing the screen, but we still cannot hear you. He is unmuted, so I don't
Probably
know
he
what
needs
happened.
to reconnect.
Yeah, let's wait for him. Then the sharing disappeared, didn't it?
Yes, please share it.
I'll reshare so he can jump in.
Can you hear me now?
Yes.
Okay.
Good.
I don't know what happened. Then I will take control now. And yes, so thank you, Mihaly. My name is Dirk with small technical issues here. I work at DNV together with Lillian, and I'm supporting the development of the scheduled data ontology. So let's talk about modeling patterns. Mihaly has shown a lot of attributes. So these are properties that associate schedule elements or items with values. And we categorize these values in planned, calculated, and observed. And some of these are being transferred when scheduled data is being exchanged. So in particular, the planned ones and the observed ones. The calculated ones may be recalculated. Maybe they are transferred as well, just to double check that we obtain the same result. Now, for each of these attributes, we treat them according to IDO, we treat them as shortcut properties. So these attributes are data properties in OWL, and they are shortcuts of a more explicit modeling pattern that provides the semantics. So we have formulated a key principle in that every shortcut property must be associated with a modeling pattern so that any usage of that property can be expanded into an explicit semantic structure. So what are these shortcut properties? An example is planned lag duration, for example, that is being associated to a dependency between two activities. And there are, of course, many more, as Mihaly has shown. For example, a dependency between two activities can have a planned lag duration of 1 hour. This is the literal value typed using the XSD data type duration. This is sufficient for data exchange. It's compact and easy to process, but the property itself doesn't really provide the full semantics. So we need a more explicit modeling pattern. Now, as we can see here, this refers to temporal information. And in order to represent temporal information, we need to employ this temporal quantity modeling pattern that we have developed together with the IDO core group. If you remember, you may have seen this in the IDO presentation earlier in this series. This led to the introduction of several new terms in IDO, the class temporal datum, the object properties has temporal region and quantifies temporal region. Their inverses together with the data property temporal value. So we use these to describe modeling patterns for our schedule attributes. Let's look at an example. And the example is about lag. You have seen this earlier when Erik talked about it. Lag is something that exists between two activities. A simple example is you pour concrete and then you have to wait for so and so much time before you can continue your operation, before you can walk on the concrete, for example, or install something on it. And then this waiting period is not modeled as another activity. It is simply modeled by just saying how long we don't have any activity. Now, the lag is associated to a link between two activities. We call it a dependency. And let's say this is our instance of such a dependency, which is typed finish to start, which is the most common type of dependency. What does it mean? It relates two activities with one another, a previous activity and a next activity. And it means it talks about the time between the end of the previous activity and the beginning of the next activity. In this particular example, the previous activity is not actually a scheduled activity, it's a milestone. The specialty about milestones is that the beginning and the end is basically the same. It's the same point in time. So here we have a particular milestone, which is typed start milestone. So we relate these two activities with one another. The milestone has a temporal region, which is a particular instant on the timeline. The following activity is a schedule activity whose beginning has a temporal region which is also an instant on our timeline. Now we can attach concrete values to these two instances. We can say that the milestone instant has a temporal region quantified as property pointing to a timestamp temporal datum, which is then carrying a temporal value of May 17, 9 o'clock. The activity that is to start following that milestone has a temporal region quantified as temporal datum, again, May 17, but 10 o'clock, so 1 hour difference. Now, in order to say that this dependency allows us to specify that there should be 1 hour difference between the end of the previous activity and the beginning of the next activity, we say that this dependency has a temporal region, which is some offset interval, which is a special type of temporal region in IDO, which then has a temporal region quantified as a lag datum, a special type of offset datum, which carries the value 1 hour. Again, we use the XSD data type to express temporal information. Now notice that given these three values, these two timestamps and the duration value, they need to be consistent with one another. This is not something we express in the ontology, but would have to be checked in addition in some kind of validation step afterwards. Now, this would be the more detailed semantic representation of what lag really means. It relates the beginning of the previous activity with the end. Sorry, the end of the previous activity with the beginning of the next activity, and by associating a certain duration value with it. And when we exchange that information, we don't want to exchange this entire picture every time. So we shortcut it by introducing shortcut relations. For example, we can go directly from the activity dependency instance to the lag datum using the relation planned lag. Or we can go from the dependency instance. I think I get some noise in the background. Okay. We can go directly from the schedule activity dependency instance to the literal value of 1 hour using the planned lag duration property. Okay, so now this is done for all the shortcut properties that are used in schedule data exchange. But this is just one example. Now let me continue to talk about work patterns. So work patterns are patterns that define when work can take place. It's basically the time period when a resource is available for work. This applies to activities, dependency links, resources, and assignments. So these different schedule elements. We have a property, a relation reserved for that called has work pattern and its inverse work pattern of. But how can we describe the work pattern itself as, say, a collection of intervals on the timeline? So here we thought, before we start reinventing the wheel, we reuse what is already there. And we came across the iCalendar standard, which is standardized under RFC 5545. It is openly available and widely used. It's a standard for describing time periods and recurring schedules. In SDO, we don't use this entire standard. We only pick out the temporal pattern language in order to describe the times for availability, such as working times, assignments of work, and times of unavailability, which are lunch breaks, public holidays, and so on. The iCalendar standard allows us to define time intervals. It allows us to describe when these time intervals reoccur on the timeline, for example, in a weekly pattern, a daily pattern, monthly, yearly, and so on. And it allows us to describe exceptions and additions to those occurrences. In SDO, we use that mechanism to describe sets of time intervals, which are then classified using the IDO interval region class. And those are then combined using operators union, subtraction, and intersection. And that allows us to model complex working calendars. On the right, we see an example. So let's say we have as working time Monday to Friday, 8 to 4 o'clock. We have daily lunch breaks from 12 to 12:30. We say we pick a public holiday, which is 17th of May. This is the Constitution Day in Norway. And we say, even though it is the 17th of May, someone needs to work from 10 to 3 for catering to make sure people have something to drink, let's say. Now we can take these different times and compute the overall time for availability of that resource by saying we take the working time, we subtract the lunch, the breaks, we subtract the holidays, and we add the special assignments of work, and then we obtain a work pattern for that resource. Okay, so with that, I will hand over to Atle. Thank you.
Thank you, Dirk. So I will talk briefly about how we work to start implementation and use of SDO. So basically what we have done is that we know that, as Erik mentioned, ShedX exchanges data between host systems, Safran, Primavera, P6, and so on. They all have proprietary data format. So the goal of our work is to represent schedules in a shared semantic standard form using SDO, ICAL, and serialized as RDF turtles. In our work, we have used AI very much, and we have come up with a tool to convert data exchange data format to RDF on SDO. So where we are now is that we are able to round trip Safran schedules using SDO, and we see that what we send is what we receive. So the tool kind of looks like this. We have ShedX transfer JSON that includes schedule information, activities, calendars, resources, profiles, and structures. By using SDO and ICAL and adding our iLab extensions based on ISO 15926 part 13, we are able to send schedule data using these three and receive them back without any data loss. And as an example, you can see that here on the left, we have our JSON file format that is used in ShedX. We have some schedule information on the top. We have a single activity in a list of activities below. And to the right, we see the same represented in turtle format using SDO and ICAL. So as we are kind of a stakeholder in the ShedX project in collaboration with Offshore Norge and Cooperate, our intention with this is to have early feedback on the ontology and make sure that we can help making it as good as quality as possible before it's submitted as an international draft. So that was all I had. So I will bring it over to you, Lillian. Thank you.
Thank you, Atle, it was great to have such a practical perspective of the work we do as well. The feedback that we get from this is really valuable also for the standardization part of the work. So to conclude, SDO is about enabling practical interoperability for schedule data. It builds on and aligns with the IDO framework and has also contributed back to its development. SDO is the first domain ontology being standardized in this standard series, and we think that represents an important step forward. At the same time, as you've seen, the focus is not only on the modeling, but also on implementation. Making sure this actually works in practice for data exchange is really important to us. Again, we want to highlight that this has been a collaborative effort between the senior planners, ontology experts, and implementation competency. And we see this as a really nice opportunity to improve how scheduled data is shared and used, and also with a potential for new possibilities going forward. And that ends our presentation. So thank you for your attention. And we are open for questions.
Yes, and I have stopped